when we are doing quadratic inequalities in two variables in particular, we do need to make sure we know how to graph quadratics because we need the whole boundary line, not just the zeros. So what are some properties of quadratic functions that we need to remember? So, well, number one, it's symmetrical. Okay, and the center of symmetry is the vertex. So we must need to graph the vertex. Okay, and we also need to draw two symmetrical points. Now they could be zeros. Zeros are perfectly fine. Okay, so if you want to find zeros, we'll have our two symmetrical points, and then we still need the vertex. Okay, symmetrical points can be found lots of different ways. We can just, once we know the vertex, we can just count. Okay, we could always go the other way around, start with the zeros and find the vertex or find the middle. Or if you already have two symmetrical points, you can always use those two symmetrical points to get to the vertex and the x-coordinate of the vertex, and we can always plug into our table of values to find the y-coordinate of the vertex. So it's really important that we use those properties. We can have the three forms. Okay, three forms are the graphing form. Okay, that's the most useful. So y equals ax minus p squared plus q. So that gives us the vertex. We also have the factored form. Okay, so that's going to be, don't forget the a, x minus m, x minus n. And the least useful, because it doesn't show a symmetry, is the general form. Okay, and the c value, there are ways to use that y-intercept to generate symmetry if you know something called partial factoring. But again, that's not necessary. We can always complete the square or do something to find the vertex. So then going the other way around, we need to be able to come up with the equation of this parabola and then establish whether it's up above or below. So first thing is, let's establish the equation of this parabola. If we have vertex, we should always use vertex form. So here we do have the vertex coordinate of -3, positive 1, 2, 3, 4, 5, 6, 7, 8, 9. So positive 9. So we should start with the vertex. The other option is if we had zeros. In this case, the zeros are not clearly evident, so we probably don't want to use the zero form. And the least desirable, using the y-intercept, well, unless you're stuck with having to use it, then we use that as the last option. Here we can apply our first option to find the boundary line, and I just plug in my x and y coordinate of my vertex. Okay, so sorry, this looks like a 9, but that's a q, right? As we give that variable a q. So there's our vertex form. We still need to solve for the a expansion compression component, so we can use one of these two coordinates. Okay, and to solve for, I can always plug in x and y coordinates into the equation. So 1, 2, 3, 4, 5, 6, y equals 6 when x equals 0. Okay, so there's my equation. So I get -3, subtract 9 from both sides, and I get 9 times a. Divide both sides by 9, I get a equals -3 divided by 9, or -1/3. Okay, I should expect a negative because it's upside down. So then my equation becomes y equals -1/3 x plus 3 squared plus 9. There I've got now the boundary line. I need to establish the inequality, so I need to decide, are my solutions below the boundary line or above? Well, in this case I can see that it's below, so then I write my inequality y is less than or equal to negative 1/3, and it's equal to because that's a solid line. If it was a dotted line, I would leave out that equal to. So it becomes x plus 3 squared plus 9. So there it is. Now, if I'm a little bit unsure of myself, I'm going to go ahead and test a coordinate, because that's always a possibility, and the point we test is 0, 0. So when I test that coordinate in my inequality, I get 0, y is 0, less than 1/3 times 0 plus 3 squared plus 9. Okay, this ends up being 9 times negative 1/3 is negative 3 plus 9 is 6. Okay, so 0 is less than or equal to 6. That's true. That must be part of my solution. And again, that green point then shows up in my solution space. So I've done this correctly. My inequality holds true.